technological progress, right? Making our devices smaller and faster.
Absolutely. It's been the engine for decades.
Yeah. Well, the thing is, we're now hitting some fundamental physics limits, in traditional electronics anyway. But what if there was a way to completely redefine how we process information? Not just by shrinking things, but by changing how we actually use electrons. That's what we're diving into today.
Precisely. And it's really exciting. We're looking at the convergence of two revolutionary quantum frontiers, spintronics and twistronics.
Spintronics and Twistronics,
Yeah.
okay.
Separately, they're incredibly powerful fields, but when you bring them together, they create this entirely new field, Moiré Spintronics. And it promises to let us engineer quantum materials in ways we've really only dreamed of before, potentially unlocking, the next generation of computing.
Wow. Okay, so our mission today then is to unpack how these geometric principles, stacking and twisting these ultra-thin materials, how that can be harnessed to control the electron's spin with really unprecedented precision.
That's the core idea.
And we'll discover how this literally paves the way for a whole new generation of quantum technologies.
Yeah.
Okay, let's unpack this. So we've long relied on electron charge for our tech, right? The basics, ones and zeros. But you mentioned spintronics takes us into a whole new dimension.
It really does.
For someone new to this, what's the fundamental shift? What's different when we move from charge to spin? And why is it potentially so powerful?
That's a great place to start. So traditional electronics, like the chips in your phone, your computer, it's all about manipulating the flow of electron charge. It's essentially turning switches on and off, representing ones and zeros. That's the basis.
Standard stuff.
Right. But spintronics, or spin electronics, adds another intrinsic property of the electron. It's quantum mechanical spin. You can kind of think of it like a tiny fundamental bar magnet. Its north pole point's either up or down. It's a binary state, just like charge being on or off.
Or another dimension.
Exactly. And the game changer here is that we can use this spin alongside, or even instead of charge. The big goal is to generate, transport, manipulate, and then detect these spin-polarized electrons all spinning the same way.
And the advantages.
Well, they're potentially huge. Imagine devices with virtually no heat generation from current flow. That means much less power consumption. Non-volatile memory that, retains information forever without needing power, and potentially incredibly high processing speeds.
That sounds revolutionary. Has it seen any real-world use?
Oh, yes. We've seen success. Giant magnetoresistance, or GMR, that was a big one, used in hard drive read heads back in the late 1980s.
I remember GMR. Nobel Prize, right?
That's the one. And that discovery then led to things like tunneling magnetoresistance, TMR, in magnetic tunnel junctions, or MTJs. And those MTJs are really foundational for magnetoresistive random access memory, MRAM, which is a technology being developed right now.
Okay, so spintronics isn't brand new, but you mentioned challenges. What's held it back? You said it relies on intrinsic material properties.
Yes, and that's been a constant challenge, actually, a fundamental roadblock, as you put it. The main hurdle is efficiently generating currents where all electrons have the same spin, a fully spin-polarized current, and then injecting that current reliably into semiconductors, which are the workhorses of electronics.
Why is that so hard?
Well, common ferromagnets like iron or cobalt, they're useful, but they only partially spin-polarize the electrons passing through them, not 100%. We dream of materials called half-metallic ferromagnets. Theoretically, they offer 100% spin polarization.
Perfect, then.
In theory. But finding robust ones that actually work reliably at room temperature has been incredibly difficult. It's a material science nightmare sometimes.
What?
Or you look at topological insulators. They have these really unique surfaces that can carry pure spin currents, which is great, but often they only function at super cold cryogenic temperatures, not practical for your phone.
Right, not ideal.
So this ongoing material search for the perfect intrinsic properties, it has really been a defining and often frustrating characteristic of spintronics research for decades. The bottleneck was the materials themselves.
Okay, so that material bottleneck is where the Twistronics revolution really shakes things up. It's about engineering matter by design, you said.
Exactly. That's the paradigm shift.
So instead of being limited by a material's intrinsic properties, like its natural spin behavior, Twistronics shifts the focus to an extrinsic property, the relative orientation of stacked 2D materials, these incredibly thin layers like graphene.
Yes, just one atom thick sometimes.
And they're held together by these weak forces, van der Waals forces. So you can stack them, almost like, transparent sheets.
That's a good analogy. And the core principle, the really mind-blowing part, is that the electronic properties of these stacked layers are dramatically altered simply by controlling the relative twist angle between them. Just a tiny rotation.
The twist changes the electronics.
Exactly. And when you stack and then twist two periodic atomic lattices, these grids of atoms, ever so slightly, something truly beautiful and powerful happens. A much larger repeating interference pattern emerges. This is what we call a Moiré pattern.
Like when you look through two window screens,
So
that kind of effect.
Precisely like that. You see a new, larger pattern that wasn't there in the individual screens. And this Moiré pattern in the material creates a new long wavelength periodic potential, a superlattice. It acts like an entirely new energy landscape for the electrons moving within the material.
The new landscape.
And the cool part is the size and spacing of this Moiré pattern, this landscape, is inversely related to how much you twist the layers. So a tiny, tiny twist creates a huge Moiré pattern, which makes the effect incredibly sensitive and tunable.
Wow. Okay.
And this Moiré landscape, it fundamentally reconstructs the electronic bands, the allowed energy levels for electrons. And that leads to a whole host of emergent phenomena, things you just don't see in the single layers.
Emergent, like unexpected.
Unexpected and often completely new properties, yes. The most celebrated breakthrough, you might have heard about this, was back in 2018. The discovery of unconventional superconductivity in twisted bilayer graphene. 2 layers of graphene, twisted.
Right, the magic angle graphene.
Exactly, at a specific magic angle of about 1.1 degrees, a tiny twist. At this precise angle, the Moiré potential dramatically flattens the electronic bands. It slows the electrons right down.
Okay.
And when electrons slow down, they start interacting with each other much more strongly. Electron interactions dominate. And that gives rise to not only superconductivity, but also other exotic states like correlated insulating states and even ferromagnetism, all in graphene, which is normally not magnetic at all.
So this wasn't just some fascinating lab result. It sounds like it was a bombshell.
It really was.
Suddenly, this simple twist wasn't just changing the structure slightly. It was like discovering a hidden master tuning knob, one that could dial in entirely new quantum phases of matter on demand. That's incredible.
It transformed the field. It really did, from finding materials to designing materials.
And it's not just graphene, right? This principle applies elsewhere.
Oh, absolutely. It's been extended beyond graphene to a vast library of other 2D materials. Things like transition metal, the chalcogenides, TMDs for short hexagonal boron, nitride, other 2D magnets. The list is growing rapidly.
Okay, so we've touched on the frustrating limitations Spintronics faces with traditional materials, right?
Mm-hmm.
The material search problem. And how Twistronics gives us this unprecedented design freedom, this tuning knob.
Mm-hmm.
But the real magic, the part that makes these two fields truly revolutionary together, is when they join forces.
Yes, the synergy.
Tell us, how does twisting materials fundamentally change the spin game? What happens when Spintronics meets Twistronics?
Well, this convergence is what has given birth to Moiré Spintronics. It uses those design principles from Twistronics specifically to control spin-dependent phenomena. The Moiré superlattice isn't just a passive background anymore, it's an active component. We can use it to actively engineer spintronal properties. It's like building a specialized playground for electrons, designing the slides and swings to make their spin behave exactly how we want it to.
Okay, designing the playground. I like that. So we know manipulating spin is crucial for devices, and that often involves something called spin-orbit coupling, SOC, but I understand there's a bit of a catch-22 there.
There is a trade-off.
Materials strong in one area are weak in another. Can you walk us through that challenge and how Moiré Spintronics offers a clever way around it?
You've absolutely hit on a core issue. SOC, spin-orbit coupling, is this fundamental relativistic interaction. It links an electron's spin to its motion, its orbit around the nucleus, and it's crucial for manipulating spins using electric fields, which is what you want for practical devices, right? Easy control.
Right. Electric fields are easier than magnetic fields usually.
Much easier. But the trade-off is this. Materials that naturally have strong SOC, which makes manipulation easy, they often have very short spin lifetimes. The spin information just degrades quickly.
So the message gets lost.
Exactly. Meanwhile, materials that are excellent for transporting spin information over long distances without it degrading, like graphene, they have intrinsically very weak SOC. So it's hard to manipulate the spin.
Damned if you do, damned if you don't.
Kind of, but Moiré Spintronics offers a way out using the proximity effect.
Proximity effect.
Yeah. By placing a low SOC material, or a good transporter like graphene, right next to in close proximity with a high SOC material like one of those TMDs or a topological insulator, you can essentially imprint strong SOC onto the graphene without sacrificing its excellent charge carrier mobility, its ability to conduct electricity well.
So you get the best of both worlds.
You start to approach that, yes. For instance, putting graphene on tungsten diselenide, a common TMD, can dramatically enhance graphene's SOC by orders of magnitude, hundreds of times stronger.
Wow.
But here's the Moiré twist. This induced SOC isn't fixed. It's highly tunable via the twist angle between the graphene and the TMD layers.
The twist angle tunes the imprinted effect. How?
It's because the twist angle controls how the electronic orbitals the paths electrons take in the two different layers quantum mechanically talk to each other, how they hybridize. Twisting changes the alignment and the overlap, so it directly impacts how efficiently the strong SOC from the TMD is transferred or imprinted onto the graphene.
It's like tuning a radio to get the clearest signal from one material to the other.
That's a really good way to put it.
That's fascinating. That the twist can act as a dial for something as fundamental as how electrons interact between layers. So can this twist angle control allow for selectively engineering different flavors of SOC? Because I know there isn't just one kind, right?
Absolutely. There are different types, and the twist angle becomes a master control for shaping the overall spin-orbit Hamiltonian, the rules governing spin behavior. For example, there's one type called Valley-Zeeman SOC. In certain graphene TMD stacks, you can make it vanish completely at a specific twist angle, like 30 degrees, just gone.
Turn it off with a twist.
Effectively, yes. On the other hand, another type called Rashba SOC, which is really important for spintronic devices because it allows electric field control of spin. That Rashba SOC can triple in strength in other material combinations just by twisting the layers from 0 degrees to 30 degrees.
Triple. That's a huge change.
It is. And researchers have even found other specific magic angles, not necessarily 1.1 degrees, where the total induced SOC experiences a sharp resonant boost. That happens when the twist creates an optimal alignment between the energy bands in the two layers. So it really shows that the twist angle isn't just a minor tweak, it's a primary tool for precisely designing how an electron spin behaves in these engineered materials. Okay, building on that idea of proximity effects, the second key mechanism is proximity-induced magnetism and how the Moiré pattern can modulate it.
Ah, so inducing magnetism now, not just SOC.
Exactly. Just as SOC can be induced, magnetic order that alignment of spins can also be acquired in a normally non-magnetic 2D material, like graphene again. You do this by placing it right next to a magnetic substrate, perhaps a 2D magnet like chromium triiodide, which we'll talk more about. This effect is driven by short-range magnetic interactions called exchange interactions right at the interface between the layers.
Okay, so you put graphene on a magnet, graphene becomes a bit magnetic. But if you twist these layers, does that induced magnetism stay uniform? Or does it also start to, well, twist?
That's where the Moiré pattern gets incredibly clever again. In a twisted heterostructure, the strength of this interfacial magnetic interaction isn't uniform at all. It actually varies periodically across the Moiré unit cell. Why? Because the local atomic arrangement, how the atoms stack up right at the interface, changes continuously as you move across the Moiré pattern.
Ah, so the interaction strength depends on the local stacking, and the stacking varies with the twist.
Precisely. This creates spatially modulated magnetism. The strength of the induced magnetic moment varies periodically on that larger Moiré length scale. What this means is that the electrons experience a Moiré potential, that energy landscape we talked about, but now it has a different depth depending on whether the electron's spin is up or down.
It's a spin-dependent landscape.
Exactly, a spin-dependent Moiré potential. This reconstructs the band structure again, but now it opens up spin-polarized mini-gaps. Tiny energy gaps that only affect one spin direction.
Okay, mini gaps.
And by tuning the overall electron energy level, the Fermi level, into one of these mini gaps using an external gate voltage, you can theoretically filter the current. You could block, say, all the spin-down electrons while letting the spin-up ones through.
Achieving that fully spin-polarized current goal.
That's the idea. You could filter it to get close to 100% polarization. And crucially, the twist angle directly controls the width and the energy position of these mini bands and mini gaps. So you have direct control over spin transport using the twist.
Okay. Induced SOC, induced magnetism. What's next? You mentioned a third mechanism, maybe the most profound one.
Yes, I think this one is perhaps the most transformative. It involves what we call stacking-dependent interlayer exchange, and it leads to the birth of Moiré magnetism. This isn't about inducing magnetism in a non-magnetic layer. This is about twisting layers of an intrinsically magnetic material to create entirely new magnetic states that don't exist otherwise.
Twisting magnets themselves.
Twisting magnets themselves. Take that specific 2D magnetic material, chromium triiodide Cray. In its bulk form, it stacks a certain way, rhombohedrally, and it's ferromagnetic, all spins align. But if you just take two layers naturally, they stack differently, monoclinically, and that stacking actually favors antiferromagnetic coupling. The spins in adjacent layers point opposite directions, canceling out.
So the stacking dictates the magnetism.
Exactly. The stacking dictates the preferred magnetic interaction between layers. Now think about twisting those two magnetic layers relative to each other. When you twist them by just a small angle, the Moiré superlattice creates a complex map of different local stacking configurations within a single, larger Moiré unit cell.
So within one Moiré pattern, you get regions that look like the FM stacking and regions that look like the AFM stacking.
Precisely. Some regions within that Moiré pattern will locally favor ferromagnetic alignment, while other regions will favor antiferromagnetic alignment. This creates a landscape of competing magnetic interactions. Imagine like a room full of people where some want to face left, others want to face right, and they're all pushing against each other locally.
Magnetic frustration.
Magnetic frustration, exactly. The system can't satisfy both preferences simultaneously everywhere. It's frustrated. And to minimize its total energy, the system settles into complex, spatially modulated spin textures, arrangements of spins that are entirely absent in the untwisted parent material.
So the twist forces the magnet into a new state.
A completely new state. This emergent, twist-engineered magnetism is what we call Moiré magnetism. The resulting magnetic states can include coexisting domains of ferromagnetism and antiferromagnetism, side by side, or even smoothly varying non-collinear spin arrangements, like spin spirals or potentially even lattices of skyrmions, those topological swirls we'll talk about. Here, the twist angle isn't just tuning a pre-existing property, it's acting as a meta-tuning knob. It literally redefines the system's fundamental magnetic rules. It's Hamiltonian.
That's pretty fundamental, redefining the rules with a twist.
A very powerful concept.
Okay, so all these fascinating mechanisms induced SOC, modulated magnetism, Moiré magnetism itself, they lead to this rich variety of new magnetic phenomena. And this forms the very basis for Moiré Spintronics' incredible technological promise, right?
Absolutely. This is where the potential applications start to emerge. We've already seen Moiré magnetism in action experimentally. Seminal experiments on twisted layers of chromium triiodide, actually twisted double bilayers, have shown exactly this coexistence of ferromagnetic and antiferromagnetic order. And this coexistence leads to a measurable net magnetization overall, something that is forbidden in the untwisted material due to its natural AFM coupling in that configuration.
So the twist creates magnetism where there wasn't any net magnetism before.
In that specific setup, yes. And crucially, this Moiré magnetic state was found to be tunable by an applied gate voltage, an electric field. This enabled voltage-assisted magnetic switching, flipping the magnetic state with voltage, not just current. That's a key goal for making ultra-low power spintronic memory.
Voltage control is the dream for low power.
It really is. There's also been a direct experimental evidence, using advanced microscopy, for non-collinear spin textures, these complex swirling magnetic patterns. And interestingly, they seem most pronounced at a twist angle of approximately 1.1 degrees in that system. Intriguingly close to the magic angle we discussed earlier for electronic properties in graphene. It suggests a deep link between electronic correlations and this emergent magnetism.
Fascinating connection. And beyond these magnetic states, Moiré Spintronics also offers new ways to create and control those topological spin textures you mentioned. Moiré skyrmions.
Yes, skyrmions.
These are the robust particle-like swirls in the spin texture, like knots in a magnetic field almost.
That's a good way to think about it. Their knotted or topological nature makes them incredibly stable and resilient against disturbances like thermal noise or defects.
Which is great for memory, right? Stable bits.
Exactly. That stability, plus their potentially tiny size, makes them ideal candidates for high-density, low-power racetrack memory where you'd shunt these skyrmions along a wire. And Moiré superlattices have emerged as a really novel and highly tunable platform for creating, stabilizing, and manipulating these exotic topological objects.
How does the Moiré pattern help with skyrmions?
Several ways. For example, the Moiré pattern can periodically modulate an interaction called the Dzhalinsky-Moiré interaction, or DMI, which is crucial for stabilizing skyrmions. This modulated landscape can effectively trap and stabilize individual skyrmions. Also, the magnetic frustration we talked about in twisted multiferroic materials, materials where electric and magnetic properties are linked, that frustration itself can spontaneously lead to the formation of skyrmion lattices.
They just appear because of the twist.
Under the right conditions, yes. And perhaps even more strikingly, theoretical work shows that in certain twisted Moiré superlattices, these intricate skyrmion textures can stabilize without needing any external magnetic fields, which simplifies things greatly. Just the Moiré coupling itself is enough.
That's huge. No external field needed.
It could be. And the Moiré platform offers potentially unprecedented control. In certain twisted multiferroic heterostructures, theory suggests an applied electric field can switch the electrical polarization, which then modifies the magnetic interactions and the Moiré landscape experienced by the skyrmions. This provides a direct pathway for all electric control writing, deleting, maybe even moving skyrmions with just voltages.
Electric control is always preferable.
Definitely. Furthermore, the periodic potential of the Moiré lattice could act like guide rails, effectively guiding skyrmion motion. This might help eliminate undesirable side effects like the skyrmion Hall effect, where skyrmions tend to drift sideways when you try to push them straight, complicating device design.
Like banked turns for skyrmions.
Sort of, yes. And we're seeing progress. Recent breakthroughs, like the observation of room temperature skyrmions, actually skyrmion bags, which are clusters in a specific van der Waals magnet without complex engineering. That's a crucial step towards practical applications. Room temperature is key.
Absolutely. And it's not just graphene and chromium triiodide, is it? This synergy extends to an incredible array of emerging material combinations.
Oh, the possibilities are vast. The van der Waals material library, all these different 2D materials you can stack it, provides this rich and largely unexplored playground for designing new Moiré Spintronics systems. We're seeing explorations of twisted bismuthine, which has giant intrinsic SOC, graphene on ferroelectric materials for huge proximity effects, looking at high-mobility 2D magnets, exploring whole new families like the MZines. It's a huge design space.
So many building blocks.
And these examples really underscore a key theme. Moiré superlattices act as metamaterials for magnetism.
Metamaterials, meaning their properties come from structure, not just composition.
Exactly, like optical metamaterials that bend light in weird ways because of their structure. Here, the magnetic properties are derived not just from the chemicals involved, but from the engineered Moiré structure on the nanoscale. It's like playing with quantum Legos, but your blocks actually warp and change their fundamental properties based on how you stack and twist them. We're literally building quantum properties from the ground up.
Building quantum properties.
This approach provides a unique platform where three of the most important themes in modern condensed matter physics, strong electron interactions, non-trivial topology like skyrmions, and electron spin, they all naturally converge. And the truly remarkable thing is they are all potentially tunable by a single, simple geometric knob, the twist angle.
Okay, let's turn to the applications. This is where the rubber meets the road. Bridging this amazing science to actual technology. How can Moiré Spintronics address the limits of conventional electronics we talked about at the start?
Right, the applications. For next-generation magnetic memory, MRAM, Moiré Spintronics offers potentially dramatic improvements. MRAM is already a leading candidate for universal memory, fast like RAM, persistent like flash.
Universal memory, the holy grail.
Pretty much. And with 2D materials in the magnetic tunnel junctions, the core of MRAM, we're seeing theoretical predictions of giant tunneling magnetoresistance, TMR ratios. That's the difference between the 0 and 1 state resistance. Predictions are orders of magnitude higher than conventional devices, meaning a much clearer signal.
Better readability.
Exactly. Then there's spin-orbit torque, SOT, devices. These use an electrical current flowing in plane to switch the magnetization of an adjacent magnetic layer, much more efficient than traditional magnetic field switching. And SOT devices made from 2D magnetic heterojunctions, especially using proximity effects, can potentially achieve magnetization switching without needing an external magnetic field and at extremely low current densities. This drastically reduces the energy needed to write information.
Less energy per bit flip.
Much less. And twist angle engineering itself can be used here too. For instance, twisting layers of certain materials can tailor their crystal symmetry to maximize the efficiency of this SOT effect. You can design the optimal SOT material with a twist.
Designing the material for the task.
Exactly. But perhaps the most transformative possibility for MRAM is voltage-controlled switching. using an electric field instead of a large current pulse to flip the magnetic bit.
We mentioned that possibility with Moiré magnetism.
Yes, and it has actually been experimentally observed in twisted double bilayer cryeros, flipping the net magnetization with a gate voltage. If this can be perfected and made robust, it promises monumental power reduction for memory. It's like replacing a sledgehammer, the current pulse, with a light switch, the voltage, for writing data. The energy savings could be astronomical.
Game changer for battery life, data centers, everything.
Potentially. And researchers are also working on fully integrated, all van der Waals MRAM cells, stacking the magnetic layers, the insulating tunnel barrier, and the SOT layers, all using 2D materials. This allows for things like decoupled read and write paths, which can enhance endurance how many times you can write to the memory.
Okay, so memory is a huge area. But beyond memory, Moiré Spintronics also promises to revolutionize spintronic logic and transistors.
Yes, moving beyond just storing data to processing it using spin, we're looking at things like spin-based field effect transistors, spin-FETs.
A transistor based on spin.
Right. And a Moiré-based spin transistor, for example, could operate via what we mentioned earlier, Moiré potential gating. What does that really mean for logic? Well, it represents potentially a new paradigm. Remember how the Moiré pattern creates different energy landscapes, those mini gaps for spin-up and spin-down electrons?
Right, the spin-dependent landscape.
So, a simple gate voltage can be used to tune the electron energy level right into one of those spin gaps. This effectively turns off the current for one spin direction while allowing the other spin direction to flow freely.
So the output current becomes purely spin-up or purely spin-down.
Exactly, or at least highly spin-polarized. This gives you a way to create spin-polarized currents on demand using just a gate voltage, which is the basis for spin logic gates, and also the efficiency of converting charge current to spin current, or vice versa, using that proximity-induced SOC we talked about. That efficiency is also twist angle dependent, so you can tune how well your device talks between the charge world and the spin world.
Tunable conversion.
Yes. But maybe the most interesting advantage here is that Moiré devices are potentially reconfigurable during operation.
Reconfigurable? How so?
Think about it. A single Moiré device could have its magnetic state written to act as memory, maybe using voltage control. And then its transport properties, how it conducts spin-polarized current for logic, could be modulated by the same gate voltage.
Processing and storage in the same place.
Exactly. This directly addresses the von Neumann bottleneck, that frustrating separation between the processor and memory in conventional computers, which causes delays and wastes energy shuffling data back and forth. Moiré Spintronics could allow co-location of processing and storage right at the material level itself.
That's a fundamental shift in architecture. Okay, memory, logic. What about quantum information? Quantum computing, that's another huge frontier.
Absolutely. And a major challenge there is qubit fragility. Quantum bits are notoriously sensitive to noise, leading to decoherence, errors.
Keeping qubits stable is hard.
Very hard. Moiré Spintronics offers several intriguing strategies to engineer more robust qubits. One idea involves excitons bound pairs of electrons and holes in twisted layers of certain 2D semiconductors. There are dark excitons, which are optically inactive, meaning light doesn't interact with them easily, which makes them long-lived and protected from some noise.
But hard to control if light can't see them.
Right. But in twisted bilayers, the interlayer coupling can make these dark excitons slightly bright, just enough to be addressed optically, yet they potentially retain much of their noise protection. These bright and dark excitons could serve as relatively robust qubits.
A balance between control and protection.
Precisely. Furthermore, the topological nature of skyrmions offers another path. A qubit encoded in the state of a skyrmion, its presence, absence, or perhaps its type, could be significantly more stable against local perturbations due to that topological protection. This might dramatically reduce the massive overhead needed for quantum error correction, which is a huge burden currently.
Topological protection for qubits.
And Moiré engineering provides a potential platform to create and electrically manipulate these topological skyrmions deterministically. Beyond qubits themselves, Moiré systems are also fantastic platforms as quantum simulators.
Dealing quantum systems.
Yes. Their incredible tunability allows experimentalists to realize and study complex quantum many-body Hamiltonians, the mathematical descriptions of interacting quantum particles like the famous Fermi-Hubbard model. These models are often intractable, too complex for even the most powerful classical supercomputers to simulate accurately.
So you build a quantum system to study other quantum systems.
Exactly. Moiré systems could also host other exotic topological phases of matter, some of which might support things like Majorana's zero modes, theoretical particles that are their own antiparticles, which are predicted to be building blocks for inherently fault-tolerant topological quantum computers.
That's deep quantum territory.
It is. And there are even ideas about using unique orbital ferromagnetic states found in graphene coupled with boron nitride as a potential form of memory for quantum computers. The possibilities are really branching out.
Wow. Okay, we've painted this truly exciting picture of potential. Memory, logic, quantum computing, fundamental science. But, every scientific frontier has its grand challenges. For Moiré Spintronics, the biggest mountains to climb aren't just in the physics, maybe, but in actually making these incredible materials reliably, at scale, and making them work outside the pristine lab in our everyday devices.
You're absolutely right to ask that. The practical hurdles are significant.
So what are they? What stands between this lab marvel and widespread adoption?
Well, the primary obstacle, number one, really lies in fabrication, scalability, and reproducibility. As we hinted, the vast majority of breakthroughs so far in Twistronics have relied on this manual, painstaking, low-throughput, low-yield process. It's often called tear and stack.
Tear and stack. Sounds artisanal.
It is. You exfoliate a flake of 2D material using sticky tape, find another one, pick one up, place it on the other, try to get the twist angle right. It's fundamentally a laboratory craft, not manufacturing. Devices made this way are typically small, often micrometer scale, and the manual process is prone to contamination dust, polymers from the tape, and also moiré disorder.
Moiré disorder, meaning the twist isn't perfect.
Exactly. The twist angle might not be perfectly uniform across the whole sample. Maybe there's strain or bubbles trapped between layers. This leads to frustrating device-to-device variation. What works perfectly in one device might not work in the next one, made the supposedly same way.
That's a killer for manufacturing. You need consistency.
Absolutely. You need yield and reproducibility.
But there must be pathways to scalability being explored, right? What are researchers doing to move beyond this craft stage?
Oh, definitely. This is a major focus. Researchers are vigorously pursuing advanced growth techniques. Things like chemical vapor deposition, CVD, metal organic CVD, MOCVD, molecular beam epitaxy, MBE. The goal is to grow these 2D materials directly, layer by layer, on large wafers, like silicon wafers used in chip manufacturing, potentially with controlled stacking or twisting already built in.
Growing them stacked and twisted.
That's the ultimate goal for some approaches. Others focus on growing large area single layers and then developing advanced automated transfer and assembly techniques. We're seeing progress here using special polymer films or stamps. There are methods being developed, for instance, at Stanford that claim centimeter-scale moiré structures with near-perfect yield and angle control using automated processes. That's a huge leap if scalable.
Centimeter scale is much better than micrometer scale.
Much better. And alongside that, crucial interface engineering is needed. Stacking the layers in ultra-high vacuum to prevent contamination, developing low-energy methods to deposit electrical contacts without damaging the delicate 2D layers. All these are vital pieces. Okay, so fabrication is hurdle number one. Oh, what else? Beyond just making them, there are challenges with material stability and operating conditions, right?
Ah, yes, the stability.
The room temperature problem is a big one, especially for the magnetic aspects. Many of these exciting moiré magnetic states, and indeed many of the parent 2D magnets themselves, only function at cryogenic temperatures, often well below 77 Kelvin, the boiling point of liquid nitrogen. Maybe even liquid helium temperatures, just a few Kelvin.
Minus hundreds of degrees Celsius.
Exactly. And for practical technology in our homes, cars, pockets, room temperature operation around 300 Kelvin is pretty much non-negotiable.
Can't carry liquid nitrogen around for your phone.
Not easily. Additionally, there's thermal and structural stability. Those very weak van der Waals forces that make stacking and twisting possible also mean the structures can be somewhat manestable. There's often a thermodynamic driving force for them to untwist or relax back into a lower energy, non-twisted state, especially during device processing steps that involve heating. This can destroy the precise moiré pattern you worked so hard to create.
So they can just unwind themselves.
They can if you're not careful, or if the structure isn't stable enough.
So how are scientists tackling that fundamental stability issue, keeping things twisted and working when warm?
The focus is really twofold. First, there's intense research into finding and engineering 2D magnetic materials that intrinsically have high Curie temperatures. The Curie temperature is the point above which a material loses its ferromagnetism. We need materials that stay magnetic well above room temperature.
Finding better building blocks.
Exactly, and progress is being made there. Second, related to the structural stability, fabricating larger Moiré structures, like the centimeter scale ones, that can actually enhance their thermal stability. The energy barrier required to initiate the untwisting process is much higher for a larger area. It's like trying to untwist a tiny paperclip versus trying to untwist a giant steel beam. The larger structure is more resistant to relaxation.
Bigger is more stable in this case. Interesting.
Counterintuitive maybe, but yes. And finally, there are the ongoing fundamental, theoretical, and experimental frontiers. We still need to deepen our theoretical understanding. Current models often treat the lattices as rigid, but in reality, the atoms can slightly rearrange or reconstruct themselves within the Moiré pattern, which can significantly affect the electronic properties. We need more sophisticated models that capture this and also handle the strong electron interactions accurately. Multi-scale models are needed.
Better maps for the territory.
Precisely. We also need to explore new tuning knobs beyond just twist angle and gate voltage. What about applying mechanical strain? Strain engineering can actually create Moiré-like patterns without any twist, or it can be used to induce phase transitions in twisted structures.
Stretching or squashing the layers.
Yes. And optical control is another exciting frontier, using light pulses to switch magnetic states or control conductivity, potentially leading to all optical devices. And, of course, continuing to expand the materials library. The number of possible van der Waals materials and their combinations is astronomical. We can't possibly test them all experimentally. So high-throughput computational screening, using computers to predict the properties of many combinations, and increasingly, AI and machine learning approaches are becoming essential tools to guide experimental efforts toward the most promising candidates.
Using AI to find the next magic angle material.
Potentially, yes, to accelerate discovery.
You know, it really sounds like a double-edged sword, this extreme sensitivity of Moiré systems. It's clearly a huge challenge for manufacturing consistency.
It is.
But it's also a profound scientific signal, isn't it?
Yeah.
Showing just how delicately balanced these quantum energies are. Could that sensitivity even be turned into an advantage?
That's a great point. While it's a headache for making identical transistors, that extreme sensitivity could be an opportunity for other things, like ultra-sensitive nanoscale metrology devices, tiny quantum sensors that could detect minute changes in electric fields, magnetic fields, strain, or temperature by monitoring changes in the Moiré pattern's properties.
Turning a bug into a feature.
Potentially. Ultimately, the path forward for Moiré Spintronics requires this deeply symbiotic relationship between theory, experiment, and materials science. They really have to work in lockstep, informing each other continuously. Theory predicts, experiment validates or refutes, materials science provides the building blocks. It's the only way we'll achieve the grand vision of designer quantum materials with truly on-demand functionalities.
What a deep dive. Seriously fascinating. We've really seen how Moiré Spintronics offers this complete paradigm shift. It's not just about finding new materials anymore, but about designing them from the ground up, layer by layer, twist by twist. It's almost like writing a complex quantum magnetic code using geometry.
That's a fantastic way to put it. And the ability to precisely engineer these fundamental properties, things like spin-orbit coupling, magnetism, electron interactions at the atomic scale, using simple geometric parameters like twist angle and stacking, it really does move us closer to a future of ultra-low power memory, reconfigurable logic that combines memory and processing, and maybe even robust qubits for quantum computing. It's truly a testament to how profoundly simple changes in structure, just a little twist, can lead to entirely new quantum realities emerging.
So just imagine a future where the next huge leap in computing power doesn't come from making transistors even smaller, but from finding just the right twist. Thinking about everything we've discussed, what stands out to you personally as the most surprising or maybe counterintuitive aspect of controlling reality with just a mere twist? And how might this whole twist in design philosophy ripple outwards? How might it influence other fields of science and engineering beyond electronics? The possibilities really do feel mind-bending.